In Chapter 8, we're again going to be looking at alkyl halides, but this time we're going to be focusing on elimination reactions. So first, let's start with the general features of an elimination reaction. It is the opposite of an addition reaction. We'll be talking about those in Chapter 10. Usually we'll find that alkyl halides will react with some sort of Bronsted-Lowry base, usually a strong base, but not necessarily. And in the process of doing that, it will produce an alkene. We lose two atoms from adjacent carbons to form a new pi bond. And so here is an example. In this case, we are going to lose the hydrogen and a halogen that are on adjacent atoms. Here is our base. Again, we'll talk about the base in more detail later. And we eliminate the H and the X from across that carbon-carbon bond to form a pi bond. So now we will have a double bond in between these two carbons. And in the process of doing that, we will get the conjugate acid of our base and, of course, our leaving group, much like what we saw in nucleophilic substitution. We have a leaving group. So let's look at a few examples of elimination. In both of these example reactions, we'll have a base that removes the hydrogen and the halogen acts as a leaving group. Here, our base is potassium hydroxide. We'll talk in more detail about what kinds of bases we need to do this. And then the hydrogen is on the adjacent carbon. And we remove hydrogen and bromine across this carbon-carbon single bond, and it forms a carbon-carbon pi bond. And then here we have the conjugate acid of our base, and then the leftover ions when we are done. This is a similar case, except on this one we have hydrogen and chlorine, and we eliminate the hydrogen and chlorine across that carbon-carbon single bond to form the pi bond. So we'll now have a double bond between those two carbons. There's our base, there's the conjugate acid of that base, and here are the ions that are left over. So now what I want to do is I want to look at a little bit of terminology and to help us identify what our products are going to be when we do this reaction. So in this chapter, we will be primarily looking at dehydrohalogenation. And this is where we remove the elements HX, where X is a halogen. And dehydrohalogenation quite literally means removing hydrogen and halogen. And it's an example of something we call a beta elimination. Now, the reason that we call it a beta elimination is that the alpha carbon, and I'll get the pictures up here, the alpha carbon is the carbon that has the halogen, and the beta carbon is the carbon that has the hydrogen on it. And so we will remove that hydrogen and halogen at the same time, and we will form a new pi bond. All right, and that will give us the alkene, the conjugate acid of our base, and a new bond between the alpha and beta carbon. And then, of course, there is our leaving group. So here are a few of the common bases that are used in dehydrohalogenation. They're typically strong, negatively charged oxygen compounds like hydroxides and alkoxides. And when I say strong, I mean strong bases. Here are a few of those. So sodium and potassium hydroxides are favorites because they are quite affordable. Sometimes alkoxides are going to be a little bit preferred because of solubility issues. And sometimes we'll want to go with something like potassium tert-butoxide, and I'll explain why that is a little bit later. But this one, it's a little bit stronger base, and it also ends up avoiding some side reactions that we don't want. Again, I will discuss that in a bit. There are other bases, strong bases that we can use. Sodium amide, which is sodium with the NH2 minus anion. All right, and that NH2 minus anion, that is the conjugate base of ammonia Ammonia, as you may or may not remember, has a pKa of 38. So when you have the conjugate base, that means it is a very strong base. All right. Water, for example, has a pKa of 15.7, so it's a strong base. Methoxide and ethoxide come pretty close to about 16, whereas the tert butoxide has its conjugate acid, tert butanol, has a pKa of about 18. Those are all pretty strong bases, but this one is even stronger. Occasionally, we have some other options, and these are often used when solubility is an issue. We can use what is called, these are strong sterically hindered nitrogen bases. They are not as strong as these other bases that we're looking at, but they are pretty strong and do not act as nucleophiles, so they don't have the risk of doing the SN2 reaction that we saw in the previous chapter. But here we go, dBn and dBu. The N is for nonane. If you look, there are 9 atoms in that ring, including the 2 nitrogens, so 7 carbons and 2 nitrogens, so that one's nonane, and this one's undecane. So the dBn has 9 total atoms in the rings, and the dBu has 11. So that's the difference. We're going to talk about those a little bit later when we talk about the different mechanisms for elimination. So to draw an elimination product, we need to first find our alpha carbon. And so here is an example. We've got 2-bromo-2-methylpropane. And so this is, this one's tert butyl bromide, if we want to look at it that way. There are 3 methyl groups that are attached to this central carbon. And so that is our alpha carbon, is the carbon that has the halogen on it. Identify any beta hydrogens or beta carbons that have hydrogens. And so sometimes we'll just refer to those as beta hydrogens. So we want to identify those beta carbons. So here's a beta carbon, there's a beta carbon, there's a beta carbon. It turns out that those are all identical. So all 3 of those beta carbons are identical because they're all methyls. All right. Then remove hydrogen and halogen and form a pi bond between the alpha and beta carbons. So in this case, we removed 1 hydrogen from the beta carbon and the halogen from the alpha carbon, and we formed this new pi bond in between the alpha and beta carbon. You'll also notice that the 2 methyls are still there. All right. Now, we didn't show the conjugate acid of hydroxide, that's water, and we didn't show the ions. That is common, that we just show what the organic products are and kind of ignore the inorganic products. In this case, we've got potassium tert butoxide is our base, which turns out to be a pretty good base. This is 2-bromobutane, so here's carbon 1, 2, 3, and 4. There are 2 different types of beta carbons that have hydrogens, and on carbon 1, we will have a hydrogen, and then here, carbon 2 is the alpha carbon, and carbon 3, we have another type of beta carbon with hydrogen. So carbon 1 and 3, so those are the 2 possible locations that we can do elimination. If we eliminate between carbon 1 and 2, so between these 2 carbons, we will end up with the 1-butene. And if we eliminate between carbon 2 and 3, we will end up with the 2-butene, Okay, and there is also a possible stereoisomer of this. We will talk about that a little bit later. So let's look at number 26. This one is pretty straightforward. So here is number 26. And draw all possible constitutional isomers. We're ignoring stereoisomers at this point. We will pay attention to stereoisomers a little bit later, but for now we are ignoring those. So all the possible constitutional isomers formed by dehydrohalogenation of each alkyl halide. So we'll count 1, 2, 3, 4, 5, 6 carbons and bromine. So I'm going to redraw 1, 2, 3, 4, 5, 6. And then that is the bromine. So our alpha carbon is carbon number 1, and we only have one beta carbon, which is carbon number 2. That means that we have to do elimination between carbon 1 and 2. So we'll just draw that 1, 2, 3, 4, 5, 6. So here between carbon 1 and 2, we will draw a double bond. And that is our only possible constitutional isomers. Since there's only one type of beta hydrogen, then that means we have only one constitutional isomer. On this one, we're going to have more than one possible constitutional isomer. And so here, I'm going to number this for discussion purposes. So 1, 2, 3, 4, 5, 6, 7, 8. So you'll see that our alpha carbon is carbon number 3. And we have beta carbons that are carbons 2 and 4. And so with carbons 2 and 4, that means that we can have, since there's two different beta carbons, we can have two different constitutional isomers. So we can get a elimination between carbon 2 and 3. So 1, 2, 3, there's an elimination there. And we can also get an elimination between carbons 3 and 4. All right, so we have a pi bond. That pi bond didn't show up very clearly. I'm going to redraw it. All right, that was ugly. Let's just redraw. All right, sorry about that delay there. All right, so again, if we eliminate between carbons 2 and 3, we will get this one. And if we eliminate between carbons 3 and 4, we will get this one. So those are our two possible constitutional isomers. Now, there are some stereoisomers. There are the cis and trans for each of these, but I am ignoring those at this point. All right, for this one, we've got 1, 2, 3, 4, 5, 6 total carbons, 5 in the main chain. So I am going to redraw this. 1, 2, 3, 4, 5. That's 5 in the main chain. And then, so 1, 2, and then on the third one here, we've got a chlorine. And on the fourth carbon, we've got a methyl. All right. So that is our starting compound. And now we need to look at what are the possibilities for constitutional isomers. So let's go ahead and number this. So 1, 2, 3, 4, 5. And there are 2 beta carbons that have hydrogens. Our alpha carbon is carbon number 3, and our beta carbons are carbons 2 and 4. So we can eliminate between carbon 2 and 3, and we can eliminate between carbons 3 and 4. So let's draw each of those products. If we eliminate between carbons 2 and 3, we will get this. And if we eliminate between carbons 3 and 4, we will get this. So those are 2 possible constitutional isomers. Now we'll look at this one. On this one, it turns out that there's only one beta carbon that has a hydrogen, and that is this carbon right here. Our alpha carbon that has the iodine, we're going to eliminate across this carbon and this carbon to make a pi bond. So that makes it pretty easy. And that is our only constitutional isomer that is possible as a product. Okay, so going back to our presentation, we want to look at the alkenes, which are our products of elimination. Okay, so The alkenes are hydrocarbons that contain a carbon-carbon double bond, one that is a single bond and one that is a pi bond. And here is the simplest example of an alkene, which is ethylene. You'll notice that ethylene has a double bond in between the two carbons, and then has 4 single bonds going to the hydrogens. We'll see that the carbons are sp2 hybridized. Each of those carbons are sp2 hybridized. And you may or may not remember, but the sp2 hybridized carbons, that means that they are planar. So that means that all of the atoms that are attached to it and that atom are in a plane. And we'll find that the pi bond causes it so that that the plane of these 4 carbons has to be the same. These 4 atoms has to be the same as the plane of those 4 atoms. And that's really best illustrated by going to a model and looking at a model. We've looked at this model before for ethylene. We've got the carbons that are here and here. There's a sigma bond, which is represented by this blue bond. That's the sigma bond. That's an overlap of an sp2 hybridized orbital on this carbon and an sp2 hybridized orbital on this carbon. And then, of course, we've got the sigma bonds going to the 4 hydrogens, an sp2 hybridized orbital on carbon overlapping with an s orbital on hydrogen. And so there are the sigma bonds. In addition to that, we've got a pi bond that is in between the 2 carbons. That pi bond is both above and below that sigma bond. And just as a reminder, a pi bond is one bond that is in 2 locations, partly up here and partly down here. And so that represents our pi bond. Okay. All right, and then here is a diagram. And as I mentioned, all 6 of the atoms, and we'll go back to that picture, or back to the model, we'll see that all 6 of the atoms here are coplanar. So all 6 of both of the carbons and all 4 of the hydrogens are in the same plane. All right, and then the bond angles come out to approximately 120 degrees. So 120 degrees. And that's typical of sp2. Now, they may be slightly different if you have different substituents, but 120 is pretty darn close. All right, classifying the alkenes. We can classify alkenes based on the number of carbons that are attached to that alkene. So alkenes can be classified, again, by the number of carbons that are attached to the carbons that are on the double bond, that are part of the double bond. So if we only have 1 carbon attached to a double bond, so we have 3 hydrogens and 1 carbon, then that is a monosubstituted alkene. If there are 2, then that is disubstituted. 3 is trisubstituted, and 4, of course, is tetrasubstituted. So here are just a few examples of some substitution patterns. This one is monosubstituted. Notice the 2 carbons here, the 2 carbons of the double bond, and there's only 1 carbon attached to that. So we don't count this carbon because it's not directly attached. So that's monosubstituted. Here we've got disubstituted. So here's the double bond, and we've got the CH2 that's part of the ring and the CH2 that is also part of the ring. On this one, it is trisubstituted, and the reason that it is trisubstituted, of course, because there's 3 carbons. So let's look at number 8.2 on the in-class assignment. We want to classify each of the alkenes in this by the number of carbon substituents. So we want to classify them as either mono, di, tri, or tetrasubstituted. So mono, di, tri, or tetrasubstituted. Let's just start with this one, and we'll just draw a line to it. We'll see that this double bond, there's 1, 2, 3, 4. So this one is tetrasubstituted. All right, here Here we've got the carbons that are attached there, and we've got one carbon here, one carbon there that are attached. You'll also notice there's two hydrogens, so this one is di-substituted. This one, there's a methyl, this carbon, and this carbon, so this one is tri-substituted. And then here we've got the carbon-carbon double bond. We've got 1, 2, so this one is di-substituted. And then this one, 1, 2, 3, that one is tri-substituted. So tetra, di, tri, di, tri. Sounds like, somebody's angry at you or something. All right. So now let's look at these. On this one, you can clearly see the two hydrogens, and then there's two carbons that are attached. So this one is di-substituted. Here on this one, we've got 1, 2, 3 carbons attached. So that one is tri-substituted. I got that backwards there, tri-substituted. And this one, 1, 2, 3, this one is also tri-substituted. And on that there are no more alkenes. There are no more carbon-carbon double bonds that we need to classify. Okay, so going back, restricted rotation. Now, you may or may not remember this, but in an alkane, we have free rotation about carbon-carbon bonds. And I'm going to illustrate that. I'm going to bring a little camera down here and illustrate that. Here, this is just ethane. I don't have a butane molecule with me, and it would be hard to get it into the camera shot anyway. But here is ethane, and you may or may not remember, but we can rotate freely about that carbon-carbon double bond. And so as a consequence, if we've got two substituents that are on these carbons, we could look down the carbon-carbon bond and determine the dihedral angle and things like that, and we can rotate about it. So alkanes have different conformations. They can have, for butane, they can have the anti-conformation and the eclipsed conformation. However, in but-2-ene, or sometimes you'll hear me call this 2-butene because that's how, well, that was a previous way that we named it. In but-2-ene, we will find that there is a cis conformation, or a cis isomer and a trans isomer. Because of the pi bond, it's not possible to rotate about this carbon-carbon bond. At least it's not possible under normal conditions. At room temperature for the alkane, you can rotate easily. In fact, it rotates dozens, if not hundreds of times a second. But in the alkene, there is no free rotation. That means if you have different atoms that are attached, and I just happen to have some different atoms attached. I don't have methyls attached, but I have different atoms. So here you'll notice the two red atoms are on the same side of the carbon. I cannot rotate about that carbon so that they become on the opposite side. Whereas here I've got where the two red atoms are opposite each other. So the one where they are closer to each other, we would call that cis, and the ones where they are further away, we will call that trans. Now, in a later chapter, we're going to discuss a better way of naming them. All right, so cis-but-2-ene and trans-but-2-ene are considered stereoisomers of each other. They are stereoisomers of each other. To look at that one more closely, so the stereoisomers of alkenes, because of the restricted rotation, we cannot easily convert. Now, I will say that it is technically possible. It is technically possible to convert between the cis alkene and the trans alkene, but you have to do it at a high enough temperature to break this pi bond temporarily, and then the pi bond can reform once you get it over into the trans conformation. Conversely, you can also go the other way, where you have some of the trans and you heat it up and you'll get some of the cis. All right, but that does not happen at room temperature under normal conditions because that pi bond is too strong to allow that rotation to occur. All right, so cis-but-2-ene and trans-but-2-ene are stereoisomers, and they are the particular type of stereoisomers that are called diastereomers. Diastereomers are stereoisomers that are not mirror images of each other. So they are stereoisomers that are not mirror images of each other. All right, whenever the two groups on each end of the carbon double bond are different, then that means that we can have cis-trans diastereomers possible. So, all right. So we've already looked at the models. We're now going to look at number 29 on the in-class assignment. I'm going to lower that camera back down. All right, so on this, we want to label each pair of alkenes as constitutional isomers, stereoisomers, or identical compounds. All right, so constitutional isomers, stereoisomers, or identical compounds. We do not have the choice of not isomers. So these are all at least either isomers or identical. We don't have the choice of just not being isomers at all. For constitutional isomers, recall that we have different connectivity. For stereoisomers, we have the same connectivity but a different orientation in space. And for identical, we have the same connectivity and the same orientation in space. On this one, it's pretty easy to figure out that these are constitutional isomers. If we look at this methyl here, there are 3 hydrogens attached to that carbon, whereas the comparable carbon over here, there are 2 hydrogens attached. If you go through and count, there are 7 carbons and 12 hydrogens in each of these, so they are isomers of each other, but because they have different connectivity, they are constitutional isomers. All right, so now for this one, for B. All right, here we've got the same number of carbons, and you'll also notice that they are connected to the same atoms. So we have an ethyl and methyl on the carbon that's on the left. We have a methyl and an ethyl on the right, and we have the same setup over here. But what is different is the orientation in space. Here you'll see that the 2 ethyl groups are opposite each other, so they are trans to each other. And on this one, they are on the same side, so they are cis to each other. That means that these are cis-trans stereoisomers or diastereomers. Now I'm just going to put stereoisomers. And below it, I will put diastereomers, because that is a little bit more specific. They are not enantiomers of each other. 1, there's no stereogenic center, and 2, they are not mirror images of each other. For this next one, we need to look carefully at each of the double bonds. All right, we'll see 1, 2, 3, 4, 5, 6, and I am going to number this. 1, 2, 3, 4, 5, 6, and I'll number this one as well. 1, 2, 3, 4, 5, 6, and we want to look at each of the double bonds. There's a double bond between 2 and 3. Also here between 2 and 3. There's a double bond between 4 and 5. Also here between 4 and 5. So we've got double bonds at the same locations. Now let's look at the cis-trans isomerism here. So we'll look at that stereoisomer. Are they stereoisomers? On the first bond here between 2 and 3, we'll see that carbons 1 and 4 are trans to each other. So that one is trans. And then here between carbons 4 and 5, the atoms 3 and 6 are trans to each other. So that one's trans as well. Over here, we've got 1, 2, 3, 4. So carbons 1 and 4 are trans to each other. And then carbons 3 and 6 are also trans to each other. That means that these are the same compound. And to prove that to yourself, just remember that the single bonds, you can have free rotation about those single bonds. And so here I'm going to take this one and rotate about the carbon 4 bond. And I am going to draw it the same way for carbons 1, 2, and 3. So 1, 2, 3, 4. But then when we rotate about carbon 3, 4, 5, and 6, and we will get a double bond there. Okay, so now that we've done that, you'll see that this is essentially the same as this. These are the same compounds, so I'm going to put identical. All right, so now let's look at this last one. And for this one, let's look at the alkene. You'll notice that we have a stereogenic center over here. And the fact that it's a stereogenic center is not very relevant. It does have the same configuration about that stereogenic center. We want to look at the carbon-carbon double bond. And you'll notice that on the carbon that's on the right, we've got hydrogen and methyl. And on this one, we have methyl and hydrogen. So those are, but they seem to be in opposite orientation. Let's check the rest of the molecule. On this carbon, we've got CH2 and CH2. Since those are identical, but have more things attached, we need to go to the next carbon. This one's CH2, but this one is CH with a methyl on it. And so therefore, this one ends up being different than this one. So these are different groups as well. You'll notice here that these, the methyl and the larger group are cis to each other, but on this one they are trans to each other. So these are stereoisomers, and we can also, of course, refer to them as diastereomers. All right, so constitutional stereoisomers, identical, and then also stereoisomers. So you want to be able to do that kind of identification. So next, let's look at the stability of the cis alkenes and trans alkenes. So cis alkenes and trans alkenes. In general, we'll find that trans alkenes are more stable than their corresponding cis alkenes. And that is because the groups that are bonded to the double bond carbons are further apart in a trans alkene, and that reduces the steric interaction. So here is a molecular model. I do not have a physical model of the trans but-2-ene and the cis but-2-ene. But we'll see that they are further apart here in the trans isomer than they are in the cis isomer. We'll find that because in the cis isomer, the two methyls can kind of interact. There's a little bit of steric interaction there. That means that we end up with, a little bit higher in energy. How much? Well, for butene, it comes out to for 2-butene, that difference comes out to 4.7 kilojoules per mole. So the difference in energy between these is about the same as the difference in energy when we were looking at conformations of butane. However, the big difference is that we can't freely rotate between these two isomers, because in order to rotate, the activation energy would be really high because we'd have to break that pi bond. So we want to look at what makes for a more stable alkene, one that has more alkyl groups attached to the carbon-carbon double bond, or one that has fewer. And we will find that the more alkyl groups that you have attached to the carbon-carbon double bond, the carbons of that double bond, the more stable it is. So the stability of an alkene increases as you have more alkyl groups. So here we don't have any alkyl groups attached to ethylene, and then we'll find that here with one alkyl group it's a little bit more stable. With two, it's more stable. Now you'll notice here that it doesn't matter whether the two are on the same carbon or on opposite carbons. They're going to be pretty close in stability. With 3 alkenes, it is even more stable, and with our 3 trisubstituted alkene, it's even more stable. And for a tetrasubstituted alkene, it is the most stable. Now, you may be thinking, well, why is that? Well, we'll find that the carbon-carbon double bonds like to accept electron density. The carbons in the double bond are sp2 hybridized, and they tend to accept electron density from the carbons that are sp3 hybridized. So here, there's a general tendency. The more S character there is in a carbon, the more it pulls electron density towards itself. So in effect, it becomes a little bit more electronegative. Well, so for alkyl groups, it more easily donates that electron density and helps to stabilize the overall molecule. So that is sort of the rationale behind it. The alkyl groups add electron density and they stabilize the pi bond. So when we're ranking the stability of butenes, if we look at 1-butene or but-1-ene, we will find that it is not as stable as the 2-butene or the cis-but-2-ene and the trans-but-2-ene. All right. And we'll find that the trans-butene is more stable than the cis-butene, and that's because of fewer steric interactions. So more alkyl substituents is more stable, and trans is more stable than cis. So let's look at number 5 on the in-class assignment. So we want to identify which of these is more stable. So here we've got 5 carbons here, 5 carbons there. On this one, it's mono-substituted, and on this one, it's di-substituted. So this one is more substituted, more stable because it is more substituted. And I circle the one that's more stable, and I'll put because it is more substituted. All right. On this one, we've got 1, 2, 3, 4, 5, 6 carbons. There's a carbon-carbon double bond between the 3rd and the 4th carbons. And we'll see that this one is the cis isomer and this one is the trans isomer. That makes this one more stable. And because the trans is more stable than the cis isomer. All right, on the next one, we've got a ring with the double bond, and here we also have a ring with the double bond. And so really all we're comparing is the number of alkyl groups. This one has 1, 2, 3 alkyl groups that are attached. This one has 1, 2 that are attached to that alkene. That makes this one more stable. And I will put because it is tri-substituted. Instead of di-substituted. All right. Well, I'm going to stop this video, even though we're only at 38 minutes. I'm going to stop this video because I want to get the next section as part of the next video.